In the last video, we looked at partial fractions. We considered 4 different scenarios. The first sort were where we had distinct linear factors in the denominator. So we had, for example, x plus 5 over x minus 1 multiplied by x plus 3. So these are distinct linear factors. I've got the linear factor of x minus 1 and the linear factor of x plus 3. We also said that this was a proper fraction. A proper fraction is where the degree of the numerator is lower than that of the denominator. So x to the first over x squared. So this was the first type. The second type is where we had, again, a proper fraction, but we had a repeated linear factor in the denominator. So if we had now x minus 4 in the numerator, and then we might have x plus 1, and then, for example, x minus 3 all squared. So this was a proper fraction. We can see we're going to have a cubic term in the denominator. We've got a linear term in the numerator, but we've got now a repeated linear factor. This is x minus 3, x minus 3. The third sort we looked at, and less common, was where we had, again, a proper fraction, but we had an irreducible quadratic factor in the denominator. Example being 2 over, and then we had x squared plus 1, and then we had now, say, x minus 3. So we can see now that this doesn't factor right here, so we dealt with that slightly differently. We've got one linear factor and one quadratic factor. As stated before, do check that you can't now write this, for example, as a difference of squares. So if this was x squared minus 1, we could write it as x plus 1, x minus 1, and we're back up to this stage right here. So this was the third sort. So again, it was now a proper fraction. We might have now 2x plus 1. It really didn't matter. It was all about this quadratic factor in the denominator. The fourth sort were the improper fraction. That is that now the numerator is of at least the same degree as the denominator. An example might be x cubed plus 3x squared plus 4 over now x cubed minus x minus 12. We can see now that the highest degree in the numerator is equal to that in the denominator. Therefore, it's improper and we'd use polynomial long division. Another example, we might have x cubed plus 2x plus 1 over now x squared minus 4x plus 7. These are improper fractions. Okay, let's go ahead and work through some different examples and look at which method we need to use. The idea of this video is to spot which of the techniques that we're going to use for any given fraction. So let's start off. We may be asked to express this in partial fractions. So in an exam question, they might say, express this in partial fractions. The question might then go on to ask you to look at integrating these partial fractions. It might ask you to look now at an infinite series expansion. Okay, so let's look at this. First off, this is proper. X and x squared. So it's a proper fraction. I'm looking at the denominator and I'm thinking to myself, I could actually factor this. So I'm going to write now 5x plus 7 over now, taking a common factor of x out, x plus 1. So at this stage now, I have 2 distinct linear factors in the denominator of a proper fraction. So I'm going to set up the identity as I did before. The identity will be a over x plus b over x plus 1. So this is what we looked at in the previous video, and this is the first scenario. At this stage, we multiply through by the denominator, and we had on the left hand side of the identity 5x plus 7. On the right hand side we had a. The x's are going to cancel to leave me x plus 1, plus b. The x plus 1's cancel now to leave me x. This is an identity. It holds true for all values. At this stage we had 2 choices. There are certainly more choices that you could deal with, but we looked at 2 choices now to find the values of a and b. The first choice was to equate coefficients, i.e. set up simultaneous equations. The second choice was to use a substitution. On this particular method, I'll go both ways so you can see now the same way as we did it before, but 2 different approaches. Let's now look at equating coefficients. When we equate coefficients, I consider now terms in x. So terms in x. So on the left hand side, I've got 5x. Then on the right hand side, I've got ax plus bx, which means that a plus b will be equal to 5. And I call this equation 1. I now consider constants. So on the left hand side, I've got 7. On the right hand side, I'm simply going to have a. I've got no constants right here. So I can see that a is equal to 7. And that's equation 2. So if a is equal to 7, we can simply go ahead and sub this in. So we can say that 5 is equal to 7 plus b. So we can see that b is equal to minus 2. So I've got my value of a and I've got my value of b. And we went ahead and rewrote now the fraction here, 5x plus 7 over xx plus 1, as a sum of partial fractions. And that sum now was the point here, which we've got 7 over now x, and then we got b, which is minus 2 over x plus 1. Now, if you weren't convinced that that was true, just go ahead and add these fractions like you did before. Common denominator, 7 lots of x plus 1 minus 2 lots of x, will give you now 5x plus 7 over x plus 1. So that was the first way. The next way was, at this stage, we do exactly the same. So up to here, we do the same. We set up our identity, but we now use substitution. As we'll see in later examples, we'll use now a technique where we've got both in action. Okay, so let's now if we let x be equal to 0. If I let x be equal to 0, what I'm trying to do is eliminate now either a or b. If I let x be equal to 0, on the left hand side we've got 0 plus 7 will be equal to a, then we can have 1 plus 0, which is 1, plus b multiplied by 0. So from this we can see that 7 is equal to a, or a is equal to 7. So I'm looking for values that are going to set these brackets or these values. So for example, if I had x minus 3, I would sub in now 3. So let's do the next one. That's going to be now, and we'll say let x be equal to minus 1. So if I let x be equal to minus 1, 5 lots of minus 1 plus 7 on the left hand side will be equal to a. As soon as I stick minus 1 in, that will now set the bracket to 0 and therefore eliminate a, plus now b lots of minus 1. So what do we end up with from here? We can see now that this is minus 5 plus 7, which is going to give me 2, and that's equal to minus b, so b is equal to minus 2. So we can see another approach. In this particular example, I think this one is nice and straightforward, but we need to be able to work between the two to have the best chance of answering these questions as easily as possible. So there we go. In partial fractions, this is what we have. Don't just write a is equal now to 7 and b is equal to minus 2. If they just ask for the values, write them down. But if you're asked to express it in partial fractions, go ahead and write it. Okay, let's look at another one. Right, what have we got? 5x squared plus 3x minus 20 over x cubed plus 4x squared. Firstly, this is proper. X squared, x cubed. The numerator is of lower degree. So let's look at this. I'm thinking to myself, I can factor that. So looking now at the numerator, I've got 5x squared plus 3x minus 20. Now in the denominator, taking a common factor of x squared out, I've got x squared, x plus 4. So what have we got here? Well, we've got now a repeated linear factor. We've got x and we've got x squared. Therefore, I'm going to write this now as 5x squared. In fact, we can just write it out here. Let's just write it out next to it. We can write this out now as follows. We can write it as, and this doesn't matter which order you do it in, we can write it as a over x plus 4. We can have now the next one, which is going to be b over x plus now c over x squared. So what we're considering now is that we've got x and we've got x squared. In general, if you have ax plus b all squared in now the denominator, this will give rise to partial fractions of the form a over ax plus b plus now b over ax plus b all squared. And if we had a cubic term, it would now be c over ax plus b all cubed, and so on and so forth. That's quite formal. If you want to have that in your notes, you're welcome to do so. But essentially, if you can understand that we need both x and x squared, then you will be fine. Okay, let's now multiply through. 5x squared plus 3x minus 20 will be now, in the identity, set to a. Now the x plus 4 is going to cancel off, leaving me x squared. Plus b, the x will cancel off, leaving me now x plus 4. So one of the x's is cancelling off. Plus c, the x squared will cancel off, and I've got now x plus 4. Now at this stage, I've got a choice. I'm going to go for the substitution. And what I'm going to do is let x first be equal to 0. So if x is equal to 0, left hand side, 5 lots of 0, plus 3 lots of 0, minus 20. Right hand side, we're going to have a lots of 0, plus b lots of 0. As soon as 0 goes in here, the whole bracket will become 0. Plus now c, and we're going to have 0 plus 4, which is 4. So what does that leave me? That leaves me now, minus 20 is equal to 4c. So straight off we can see that c will be equal to minus 5 when we divide both sides by 4. Okay, so that's x is 0. What I'll say now is let x be equal to minus 4. So when x is equal to minus 4, left hand side, I'm going to have 5 lots of minus 4 squared, which is 16. Plus 3 lots of minus 4, and then we're going to have now minus 20. Right hand side, subbing in this time minus 4, we're going to have now a lots of 16. Just consider square minus 4, that will give us now 16. The bracket with b is going to cancel, and the bracket with c is going to cancel. So what do we have here? We have 80 minus 12 minus 20 is equal now to 16a. So what's that give me? That's 32. 48 is equal to 16a, and we can say that a will be equal to 3. Okay, so that's done. That's got that sorted. So we found now c, and that's minus 5. We found a. Now I've got no more values that are going to set these to 0. Therefore, I need to go back and start equating coefficients. So as stated earlier in this video and the previous video, we need to jump between a range of techniques if we're going to go for this approach right here. So let's now consider what we want to find. We want to find b. So if I look at this, looking at the constants is going to be no use because I've got no constants for b. If I consider now terms in x, then I could go for b and c, or if I look now at terms in x squared, that's going to probably make my life slightly easier. So what I'm going to say then is terms in x squared, and I'll just write it here so we can still see them. In general, you'd write this below. So terms in x squared, left hand side 5, right hand side a plus b. Now I already know from here that a is equal to 3, so 5 is going to be equal to 3 plus b, so we can see b is equal to 2. So I've now got my 3 values, and I can put these back in just here. So I've got now a is 3, so we're going to have 3 over x plus 4, so let's write this in, 3 over x plus 4. Then the next one I've got b is 2, so that's going to be plus 2 over x, so plus 2 over x, and then we're going to have c, which is minus 5 over x squared. And now I've expressed that single fraction as a sum of its partial fractions. So we've gone ahead and worked through that and found this like so. Now again, if you were asked to integrate this, this becomes really quite straightforward. If you haven't done integration yet, it will mean very little to you, but if you wanted to integrate this, what we've got is the integral of 3 over x plus 4 plus 2 over x minus 5, and then you could say that this is x to the power of minus 2. So say we were integrating this now with respect to x. This is going to give me a log function, and we could simply say this is 3 the log of now the modulus of x plus 4. This one is going to be plus 2 lots of the log of the modulus of x, and then raised by a power, divide by the new power, we're going to have plus 5 over x plus a constant. So I've gone from quite a tricky fraction right here to integrating partial fractions to get a fairly straightforward integral. As stated, if you're watching this, you might not have even got to this stage, and that's perfectly fine. But if you've done integration, you can see now that this is significantly easier in this form. Looking ahead at that, I'm thinking that looks a complete mess, and I don't really know how to deal with it. Once it's in this form, we can deal with it. Okay, let's move on and look at something else. I've got x squared plus 2x plus 9 over x squared plus 4x minus 5. Straight off I'm looking x squared and x squared, this is improper. So what I need to do is consider dividing this out to get a quotient and remainder. I'm also just looking ahead and I'm just thinking to myself that that does actually factor. This denominator does factor right here. So let's just look at this. Let's just write this out. X squared plus 2x plus 9 over, and if I factor this, I'm going to have what we're going to have, x plus 5 and x minus 1. So in the back of my mind, I'm just looking at this now and thinking I'm going to need now algebraic long division or any other technique now to express this as a quotient and remainder, or if you like, a mixed fraction. So let's go ahead and do that. X squared plus 4x minus 5 into now, and we'll have x squared plus 2x plus 9. So x squared into x squared goes once, or if you like, what's x squared divided by x squared? The answer is 1. 1 times x squared, 1 times by 4x, and then 1 times by minus 5. Subtracting downwards, we're going to have 0, minus 2x, and then plus 14. Okay, so I can now express this as a quotient and remainder. Here now is my quotient, here is my remainder over now x squared plus 4x minus 5. So I'm going to write this now as 1 plus, and I'm just going to write this backwards, 14 minus 2x over x squared plus 4x minus 5. But I know I can factor that, so I'm just going to write it like so. So what I've got then is x plus 5 and then x minus 1. If you need to review algebraic long division, check out my site here, there's plenty of tutorials on it. Okay, so now all we've got to do is find this in partial fractions. I've got this value of 1, we can leave that alone. So let's deal with this and then we'll bring back the 1 shortly. So writing an identity, 14 minus 2x over x plus 5 multiplied by x minus 1. We'll have now on the right hand side our identity will be simply now we've got distinct linear factors of now a proper fraction. So it's just going to be x plus 5 and then we'll have now x minus 1 plus b over x minus 1. So multiplying through, let's go ahead and multiply through, let's get some space. Multiplying through, we're going to have now on the left hand side, we're going to have 14 minus 2x. And then on the right hand side, we're going to have a, the x plus 5s are going to cancel, x minus 1. And then plus b, the x minus 1s will cancel, x plus 5. At this stage, I can now either sub in or I can equate coefficients. It's entirely up to me. I'm going to equate coefficients, but you're welcome to try 1 and minus 5 for x and then just go ahead and solve. Okay, let's now consider terms in x. So if we think about now terms in x, on the left hand side minus 2, and that will be equal to a plus b. And I'll call that one equation 1. If we look now at constants, let's look at the constants. On the left hand side now, 14 will be equal to minus a plus now 5b. So that now becomes equation 2. If I add 1 and 2, we can see now with the coefficient of a being the same, 1 plus 2, I'm going to end up now on the left hand side with 12. So minus 2 plus 14 is 12, and then 6b. That works out quite nicely that b will be equal to 2 when I divide both sides by 6. Now if b is equal to 2, subbing it in right here, minus 2 is equal to a plus 2. We can see from that, and in an exam do show you working, a is going to be equal to minus 4. So that's what we end up with. So subbing in b is 2, a plus 2 is minus 2, so a is minus 4. So we could now write this, and I prefer to write the positive value first. We can say that this is going to be 2 over x minus 1, and then we're going to have minus now 4 over x plus 5. So that's this part alone. But remember, we still have the 1 from before. So we can write this now as 1 plus 2 over x minus 1, and then minus 4 over x plus 5. And I've now expressed that as a sum of its partial fractions. So we've used now polynomial long division to take this, which is an improper fraction, as the power of x here is the same as the one here. If this was x cubed and this was x squared, improper. If this was x to the fourth and this was x to the power 2, improper. If this was x and this was x squared, proper. So improper, we're going to divide out quotient and remainder. So here's our quotient, here's our remainder, or if you like, a mixed fraction. And then we just go ahead and apply now the partial fractions part on the remainder. So there we go, nice and straightforward, 1 And again, if you wanted to test this, say I said now combine this fraction right here. Let's just go ahead and do it. Let's say x minus 1, x plus 5, and then that would be my common denominator. I want one lot now of, I'm missing the x minus 1 and the x plus 5. Then I've got plus 2. I'm missing the x plus 5, so the x plus 5. And then I've got minus 4. I'm missing now the x minus 1. So if we go ahead and expand all this out, what we're going to have here is x squared. So we've got x squared. We're going to have plus 4x, so plus 4x, minus 5, plus now 2x, so plus 2x, then we're going to have plus 10, then we're going to have now minus 4x, and then we're going to have plus 4, all over now x minus 1, x plus 5. So what have we got? The x squared, that'll stay there. We've got now plus 4x minus 4x, which is going to cancel, plus the 2x. We've got now minus 5, plus 10, plus now the 4, which is going to give me plus 9. And if I expand now the denominator, we've got x squared plus now 4x minus 5. And if we go back now to the question, what we've got in the original question is exactly that. So you can see now, if you were unsure about this, if you didn't believe it, hopefully now you can see working backwards and forwards between the two, it gives us exactly the same answer. So this is of the sort now where we have an improper fraction. So this was scenario 4 that we looked at. Now it's not as if in a textbook it's going to say scenario 1, scenario 2, 3 and 4. These are not universal terms. They're just me expressing different scenarios so you can get an idea of what you're doing. Don't go to your teacher and say, is that a scenario 4? They'll probably laugh at you. Well, probably wouldn't laugh, but you kind of see where we're going with that. Okay, let's now look at this one. This one here, well, what have I got? Well, I've got a linear factor in the numerator, and I've got a quadratic. So straight off, we can see now that the denominator is of a higher order than the numerator. So that is now a proper fraction. I'm looking at this thinking, well, I think I can factor the bottom. 8 times minus 3 is minus 24, which would give me 12 and 2. So the first thing I'm going to do is actually factor this. So it looks a bit of a mess at the moment, but let's go ahead and factor this. 2, then we're going to have x plus 5. Now in there, if I factor that, what am I going to get? 2x plus 3? Let's try this. 2x plus 3, and then 4x minus 1. Let's check that I've got that right. Yeah, I'm pretty happy that works. So what we've got now is the scenario. I've factored the bottom, and we've just got these two distinct linear factors. So we're back to scenario 1. And we can just set up the identity from here. A over 2x plus 3, and then we'd have plus now b over 4x minus 1. Now at this stage you might think, well, does, you know, I'll put it the other way around. It doesn't matter. You might have a over 4x minus 1 and b over 2x plus 3. It really doesn't matter at this stage. We're setting up an identity. We're solving now for a and b. So multiplying through, we've got 2 the quantity x plus 5, and then we're going to have now in our identity a, then we're going to have now the 2x plus 3s will drop off, 4x minus 1, plus b, the 4x minus 1 will drop off to give us 2x plus 3. So at this stage now, all I need to do is find a and b. Okay, so we could use substitution. My one concern with substitution here is that we're going to have a quarter here and then minus 3 over 2 here. And that can often lead to arithmetic slips. I think that's the most diplomatic way of putting it. So what I'm going to do now is just equate coefficients. So I'm going to look now at terms in x. So terms in x, 2x, so we can say 2 will be equal to 4a plus 2b. Or if we like, we can divide by 2 and say 1 is equal to 2a plus b. So that now is equation 1 in any form. Okay. If we now look at the constants, or terms in x to the 0, constants we're going to have on left hand side 10, on the right hand side minus a plus now 3b. So they're constants, and I'll call that equation 2. So if we just look at this, let's multiply equation 1 by 3. So let's say 3 is equal now to 6a plus 3b. So that's equation 1. Equation 2 we can leave in its current form. Let's just say 10 is equal to minus a plus 3b. Now if I subtract downwards, minus 7 will be equal to 7a plus 0. a will be equal to minus 1. So straightforward simultaneous equation, and I can just plug this back in. So if we consider plugging it back in, we can put it back in any one we want. If I put it back into equation 2, we can see that 10 is equal to minus a, which is 1, plus 3b. That works out quite nicely. 3b is 9, b is 3. So we've now got our values. So all I've done is just considered now subbing these in and then going ahead and solving. So what I can now do is write this, and again I'm going to put the positive term first. I'm going to say now that this will be 3 over 4x minus 1 minus, now we're going to have the 1, which is a, minus 1 over 2x plus 3. And if you're still not convinced now, just consider 3 lots of that minus 4 lots of that is going to give us 2x plus 10. So there we go, nice and logical, nice and straightforward. Again, if I'll just quickly do that rather than me showing that. So 3 lots of 2x plus 3 minus now 1 lot of 4x minus 1. We're going to have now 6x plus 9 minus 4x plus 1. And you can see now that gives us 2x plus 10, or 2, the quantity x plus 5, over the common denominator. Okay, let's have a look now. What have we got here? Oh, we've got now, this is going to be a proper fraction. We've got now this repeated root. So we've got, repeated factor, I should say, repeated factor in the denominator. So let's go ahead and deal with this right here. So we've got now 3x squared minus 7x minus 4. So we can set up an identity. So 3x squared minus 7x minus 4. Over now, so this is scenario 2. We've got now a proper fraction where we've got repeated linear factors in the denominator, and the repeated linear factor is the x minus 2. Just consider, if I square this out, I'm going to get a squared term, multiply it by the x, I'll get a cube. Therefore, x squared over x cubed is proper. So let's do this, x minus 3, and then x minus 2 all squared. So identity coming up, a over now linear factor x minus 3, plus b over now linear factor of x minus 2, and then plus now c over linear factor of x minus 2 all squared. When I say linear, it just means that that's x to the first power rather than x squared, which is quadratic, or x cubed, which is cubic. And we saw that if we had now in the denominator ax plus b to the power now of 2, this would give us now partial fractions of the form a over ax plus b plus now b over ax plus b all squared. And again, if this was cubed, you'd have c over ax plus b all cubed. Okay, let's multiply through. 3x squared minus 7x minus 4, and then on the right hand side for our identity, x minus 3 is going to drop off, x minus 2 all squared, plus b, x minus 2 will drop off, so we'll still have 1x minus 2, and we'll have the x minus 3. So x minus 3, x minus 2. So simply now cancelling the common factors. Plus c, x minus 3. Okay, at this stage I'm going to let x be equal now to 2 and x be equal to 3. So what we'll say, let x be equal to, let's start with 2. So left hand side, 3 lots now of 4, minus 7 lots of 2, minus 4. Right hand side, that's going to be now 0. And I'll put a lots of 0, plus b 0. Again, this will cancel off, plus c, and we're going to have 2 minus 3, which is minus 1. So what does that leave me here? I've got now 12 minus 14 minus 4 is equal to minus c. So that's minus 18 plus 12, that's minus 6, and minus 6 is equal to minus c, so c is equal to 6. Okay, so we've done that part, that's cool. Let's now let x be equal to 3. So now if we let x be equal to 3, so x be equal to 3, over here we're going to have 3 lots of now 9, minus 7 lots of 3, minus 4. Now if on the right hand side I sub in x is 3, we're going to have a. So 3 minus 2 is 1, 1 squared is 1, plus b, if I sub in with 3 I'm going to get 0, plus c, sub in for 3 is 0. So what have we got? 27 minus 21 minus 4 is equal to a. So what's that give me? A is going to be equal to 2. Okay, so a is equal to 2. Now again, we're left in the scenario where we bottomed out at values that are going to set these equal to 0. So all I'm going to do at this stage is now choose which of the terms I'm going to equate. I could look at constants. Again, I'm going to get 3 terms. I could look at terms in x. That's going to get messy. So what I'm going to consider are terms in x squared. So terms in x squared. Left hand side, 3. Right hand side now, I've got a plus b. They're the terms in x squared. Ax squared plus bx squared. I've not got c. I've not got an x squared term for c. Now we know that a is equal to 2. So we can say 3 is equal to 2 plus b. And that works out nicely that b is equal to 1. So we've now got a, b and c. 2, 1 and 6. And we'd simply put those in. So a is going to be 2. B is going to be 1 and C is going to be 6. So you'd write this now as 2 over x minus 3 plus 1 over x minus 2 and then plus 6 over x minus 2 all squared. And we've now written that in partial fractions. I will spare you working the other way. I'm hoping now that you are convinced that this does work. So in partial fractions we have the sum just here. Okay, let's move on and look at this one. So this time, now we've got 2 over x minus 1 multiplied by x squared plus 1. This is an irreducible quadratic factor. Now this is the third scenario we looked at when we had a proper fraction, but we had this quadratic factor in the denominator. And as I stated in the last video and at the start of this one, it's less likely that you're going to see this type, but we may as well deal with it anyway. Now when you've got this, if this had been x squared minus 1, then I could have expressed that as a difference of squares and said x plus 1, x minus 1, and then gone ahead and dealt with that. But as we can't, we have to now consider a different approach. Now in general, if we have in the denominator a quadratic factor of ax squared plus bx plus c, then what we're going to have now as a partial fraction is ax plus b over the quantity ax squared plus bx plus c. Again, quite formal, but if you wanted it, it's there. So let's go ahead and write this now. What we're going to have then is 2 over x minus 1. X minus 1 is a linear factor. Then we've got our x squared plus 1, which is a quadratic factor. And I'm going to write this now as an identity as ax plus b over now, we're going to have the ax plus b over x squared plus 1. And then what we'll have is plus c over the linear factor of x minus 1. So let's go ahead and multiply out. I'll just get rid of this for now and we'll just multiply through. So at this stage now, on the left hand side, when multiplying through, my identity will be now on the left 2, then we're going to have the following. The x squared plus 1 will cancel. Ax plus b multiplied now by x minus 1. If we now consider, we're going to have plus c, and then the x minus 1 will cancel, and we'll have x squared plus 1. Okay, so let's see how we can deal with this. Now, plenty of different approaches, but let's just think about now what we've got here. We've got now a bracket we can never set to 0. I can't find a value now of x squared plus 1 that's going to be 0. The first thing I can do though is if I let x, and I'll write this here, let x be equal to 1. If I let x be equal to 1, this bracket will cancel. So we'll have 2 is equal to ax plus b multiplied by 0. So straight off that allows me to find c. As subbing in for 1, I'm going to get 2. So from this we can see that c is equal to 1. Now at this stage I can just go ahead and equate the terms. So I can equate coefficients. So if we now look at terms, and I'll write this down, terms in, and we've got a choice. I'm going to start with x squared. Terms in x squared. So on the left hand side we've got 0. On the right hand side, if I expand this out, I've got ax squared, and then I've got plus cx squared. So I can say a plus c is equal to 0. Now we already know that c is 1, so 0 is equal to a plus 1, and we can see from here that a will be equal to minus 1. Okay, now let's consider we need to find b. So if we look at b right here, what we can do is consider terms in x. So I'm going to write here, and this is one approach, we can write terms in x. So if I consider terms in x, on the left hand side we've got 0, so we can write now 0. On the right hand side, c is not going to give us 1, so what we've got then is bx minus ax. So I can write that this is going to be now bx minus ax, so I've got b plus now, let's just write this out, b minus a. So if I now sub in that a is minus 1, I've got 0 is equal to b minus minus 1, b is going to be now minus 1. So all I've done is subbed in my a. Hopefully I made sense in saying that, and we end up with that scenario. Okay, so let's put this back together. So I know that a is minus 1, b is minus 1, c is 1. So I can sub these in. So what we're going to get then is minus x minus 1. Those are the values right there. A is minus 1, so I'm going to get minus x minus 1 over x squared plus 1, and then we're going to have plus 1 over x minus 1. Now I prefer to tidy this up a little and just rewrite it. I'm going to write 1 over x minus 1, and then I'm going to take out the negative factor here and have x plus 1 over now x squared plus 1. I just think that looks neater. Now again, if you decided, just said to yourself, oh actually I want to, I'm not really convinced that works, just go ahead, common denominator, x minus 1, then x squared plus 1. Numerator, we're going to have one lot of x squared plus 1 minus now this right here, which is going to be the product of these two, which is going to be x plus 1, x minus 1, which is x squared minus 1. And we can see now, when we expand this out, we're going to get x squared plus 1 minus x squared minus minus 1, which is plus 1, all over now x minus 1, and then x squared plus 1. So you can see the x squared is going to cancel and leaves us now 2 over the quantity x minus 1 multiplied by x squared plus 1. And that now sorts it out for us. So as you can see, that works all very nicely, and we can just deal with this case now when we have a quadratic factor that we can't now factor any further. So there we go, some more work with partial fractions. We've looked at the 4 scenarios and we've gone through a range of different cases. There will of course be slightly different examples of this, but ultimately the first question you ask yourself, is it proper? If it's proper, consider if you've got now the distinct linear factors in the denominator or you've got a repeated linear factor. Then say to yourself, if I've got a quadratic one, if I have, just set up this identity and go ahead and solve.